Hey NeuroTechX, I'm Chris.
And I'm Avery.
And we're the founders of WATOLINK. We started nearly a year ago with almost no neurotechnology experience. Given the competition theme, we decided to learn more about how visual BCIs for communication work, specifically those using the SSVEP paradigm.
So right now, you might be wondering, what is SSVEP? The acronym stands for Steady State Visually Evoked Potentials. What that actually is a bunch of responses we can pick up from the brain when the user is staring at visual stimuli on a screen. So let's say the user is looking at the screen with a 12 Hz flashing stimuli. If they're staring at that 12 Hz light, we can pick up a 12 Hz response from their visual cortex.
So ultimately, we can have a correlation between the frequency of the EEG as well as the frequency of the stimuli. And that correlation is what lets us control the interface.
We can figure out what letter or word the user was looking at, and then speak for them.
Hey Ivan, are you sick and tired of being our lab rat?
Yes.
Typically, these interfaces are used for people who have communication disabilities or who can't actually speak. What we found from existing SSVEP research is that information transfer rate is one of the largest bottlenecks for these systems. What this actually means is that those people with disabilities that are using an SSVEP interface won't actually be able to communicate at the same rate as their able-bodied peers, which places a clear limit on their quality of life. We propose a novel implementation of an SSVEP speller that's paired with an autocomplete system as well as a large language model to improve information transfer rate.
It supports multiple different BCIs, including Unicorn Hybrid Black and OpenBCI.
Our speller is also social media enabled and uses a text-to-speech system that can be tailored to the user.
Our purpose was to develop mechanical solutions to improve data collection with different brain-computer interface systems. Our main problem space was that the GTEC system had a fabric cap that didn't allow us to use for multiple head shapes. We solved this by creating a screw-like system that allows the GTEC electrodes to fit inside an open BCI frame.
With several adaptations to suit our team's needs in collecting EEG data from the occipital lobe. We printed the half headset in PC ABS for flexibility and durability. And attachment points were added to allow for the Velcro straps which you see in the current model. This also decreased weight on the user's head, allowing for added comfort. Comfort was a key factor in the design, as MEC was originally brought in to focus on the adaptation of the headset to several user head sizes.
Initially, when we were creating electrode adapters, we focused on a 4-piece standoff system. While symmetrical, it wouldn't allow for the tolerancing to fit the plate. From there, we moved to a ring system that would hold the electrode plate in place via height tolerancing. However, this created a couple errors. In our third iteration, we solved all those errors in tolerancing and focused on reducing the cost of the initial electrode adapter so that it could be scalable in the future.
In the past year, our sub-team has focused on conducting independent research and executing literature reviews to identify best practices for collecting SSVEP EEG signals.
Our first goal was to research different experimental conditions for data collection. Some factors that we researched included distance of the participant from the screen, as well as size, color, and frequencies of the stimuli, and interstimulus distances.
There existed several iterations to the experimental procedure, particularly with regards to the length of trials, stimuli exposure, and break periods.
The following is WATOLINK's data collection experimental procedure. The experiment takes place in a dark room where participants are placed 30 centimeters with respect to their eyes from the screen where the stimuli were presented. Participants were asked to avoid blinking or sudden movements during stimuli presentation, and to concentrate and maintain good posture. Stimulation and break periods were presented 5 seconds each, and there are 8 stimulation periods per trial. 5 trials were completed, and within each trial, 8 stimuli were cued in a random order. There was a 2-minute break in between trials in order to prevent visual fatigue.
So after we collect an individual's data, that data gets sent into a CSV with stimuli markers. That data can then get ingested by one of our notebooks, and we can visualize it to validate its quality.
To do that, what we do is we take all of the trials separated by their stimulus markers. For each trial, we'll perform principal component analysis across every one of the EEG channels, taking the most important component in terms of statistical variance and contribution to the data. We look at the spectrogram of that, treating it as a new EEG channel.
One of the other ways we visualize this is by taking each channel, getting the fast Fourier transform plot of each channel's response to a stimuli, and getting the average of that across trials.
Looking forward, future research could progress towards minimizing stimuli fatigue.
Additionally, during the data collection process, using the gold cup electrodes in tandem with the open BCI system gave good quality data. With the G-Type, we didn't need nearly as much setup time in comparison, however our signal quality wasn't as clean. Future research with this regard would work towards the minimizing of the setup time for a more easily reproducible setup, and sourcing out electrodes that can yield a high signal-to-noise ratio without the need for conductive pacer gel.
Our team's initial task was to stream EEG data from the brain-computer interface. We used the BrainFlow Python module to help interact with the board. We chose BrainFlow as it was compatible with multiple boards with minimal code changes, which proved to be very useful in our final system. This system has 3 layers: the EEG streaming layer, the data processing and AI layer, and the user interface layer. A couple of our notable decisions were deciding to use sockets to transfer data, making each of our layers into a process, and using PyQt threads and signals to interact with our UI without clicking a button. The EEG streaming layer interacts directly with the board, and it collects data using the method that we initially developed with BrainFlow. It sends this data once the BrainFlow buffer reaches 250 samples, or 1 second's worth of data. The next layer is the data processing and AI layer. It receives data from the EEG streaming layer, and either adds it to a NumPy array to be processed, or discards it. This decision is controlled based on the signals sent from the user interface, indicating whether the stimuli are on or off. We only want to store data when the stimuli are on, and we want to discard any data received when the stimuli are off. When this requirement is met, the EEG data is passed through AI functions and returns a frequency prediction. This prediction is then sent to the UI layer using sockets. The third and final layer of our system is the user interface layer. There are 2 spots where data is transferred in the UI. The first is the onset-offset control thread. Whenever there is a change to the status of the stimuli, a dictionary is sent to the data processing and AI layer over sockets. Whether the stimuli is on or off is sent along with what page the UI is currently on. The second spot where data is transferred is a frequency prediction value sent to the UI layer from the data processing and AI layer. This frequency in the context of the page is used to decide what button the user was looking at and what action the UI should take.
Before we apply any feature extraction or classification techniques, we need a way to pre-process our raw EEG data. Our stimulus frequencies lie only between 8 Hz and 15 Hz, which means that we can apply a bandpass filter and remove any irrelevant components.
Initially, to keep things simple, we wanted to get good results using a supervised user-dependent model. Using a dataset we collected in-house, we trained a CNN with magnitude spectrum features from EEG signals and input. Some of the issues we faced with the CNN model was that it was particularly computationally expensive and it didn't effectively generalize to multiple different people. In order for our system to be easily reproducible, we needed a technique that didn't require training, was computationally efficient, and could scale to multiple different people easily. One technique to do this is using CCA, or a canonical correlation analysis. Simply put, it attempts to find maximum correlations between 2 sets of vectors. In our case, one of these matrices is the EEG signals, and the other are reference signals that are traditionally chosen as sine waves of the particular frequencies that you're studying. In our in-house testing, CCA had poor accuracy. The question now remains, how do we better use CCA and get more performance without requiring a supervised model? This is where literature shows us filter bank CCA, which computes correlations not just on the base frequencies, but also their harmonics. Using FBCCA meant that we needed to toss out our simple bandpass filter. Instead, we would decompose the EEG signal into multiple frequency subbands. We can detect the harmonics contained in the subbands, which then can help us analyze the correlation coefficients between harmonic reference signals. FBCCA ended up yielding about 85% when we tested across multiple subjects with live demos. By default, our system uses FBCCA to make predictions, but for those who want a tailored experience for their own EEG characteristics, we offer the tools for data collection and training for FBCCA KNN models.
There are existing packages like Cyclopede that provide us with SSVEP stimuli. However, these tools are difficult to customize and integrate with other packages, so we opted to develop our own visual stimuli using PyQt5 and OpenGL. The current layout of the interface allows a user to select their preferred mode of output and then stay in it until changed, assuming they want to stay in a speaking mode or they want to continue to send tweets while they're in Twitter mode.
WATOLINK is able to communicate with Twitter through the Twitter API and the TweetPython library.
We also use Kokui AI text-to-speech to generate synthetic voices. We can do this by training the custom models on existing audio files of the user, giving the user more personalization within our application. There are two main ways to communicate using the interface, using a keyboard or by answering yes/no questions.
For the keyboard, the user is greeted by word and phrase suggestions for quick messaging. Autocomplete is great, but it can't work if our program isn't aware of the prompt given. It would be very tedious for the second user to have to manually input their prompt into the device that the primary user is using. Instead, we developed a React web app that a second user can access on their phone and use either speech to text or simply type and send a message to the primary user through WebSockets. Once the message is received, we can then leverage GPT-3 and our corpus to make context-aware phrase and word suggestions.
It's really exciting to be able to tweet with my brain for the first time.
Hey, what's your name?
If more customization is needed, they can toggle to a character keyboard. This character keyboard uses grouped characters and has 3 layers in order to include all the numbers and letters for 36 keys in total.
Jared.
Hey Jarrett, how do you feel about the weekend coming up real soon?
I feel great about it. I love having weekends off to relax and do whatever I want.
What are your plans this weekend?
I am going to go out and enjoy the weather.
You want to go grab a bite to eat sometime this weekend?
Sure, that sounds great. Let me know when and where you'd like to meet up.
All the demonstrations you saw in this video used the unsupervised FBCCA model. Preliminary results show our system can generalize to multiple people, which is great because all the design choices we made were with scalability and reproducibility in mind. Our system also performed well in different lighting environments. In the example you just saw, our system was able to achieve an average words per minute rate of 22 words per minute. This is over 2 times what we found to be the highest average words per minute rate from literature we reviewed, proving that large language models can successfully help improve ITR for these systems. This approach, however, still has its limitations. The main one being that messages requiring personalization could not take advantage of GPT-3. More work can be done in the future to improve phrase suggestions by taking into account personal characteristics. Additionally, more work can be done to improve latency and shorten onset-offset times to improve selection time. We should be able to reduce the onset-offset periods from 5 to closer to 2 seconds, while maintaining model accuracy. A massive thanks to everybody on the team and everyone who supported us to make this project a reality.